Alright, so let's look at our system in negative feedback. So we'll start simply by looking at the magnitude plot of the gain. Okay, so we're plotting this versus log of frequency, and what we see here is, and this is just our op-amp gain. We haven't included negative feedback yet. So our op-amp has a gain that's A sub 0 at DC at a frequency omega h. I guess we're plotting this over log of omega, not log of f. At a frequency omega h, the gain starts to roll off. It rolls off at minus 20 dBs per decade and hits a unity gain, or 0 dBs, at a frequency omega t, the transition frequency, or the unity gain frequency, as we call it. Now, let's say that we close this in negative feedback. Well, what happens if we enclose this in negative feedback is the gain is reduced. So the gain becomes, I'll try to do this in a dotted line, the gain becomes A prime, say, at DC. It's reduced from the value of the op-amp gain by 1 plus the feedback factor, so this distance is 20 times the log of 1 plus t sub 0, where t sub 0 is the loop gain, which, if you recall from the previous lecture, was equal to beta times A sub 0, and the distance from 0 dBs up to this point, A sub 0, is equal to 20 times the log of 1 divided by beta, our feedback factor. Now, once the line hits the frequency response of the original amplifier, it follows it. So we see a new pole frequency, which we'll call omega h prime. So let's look at what the gain with feedback, what happened to the gain with feedback. So first, the closed loop gain is reduced from the open loop gain by a factor of 1 plus t sub 0, and we showed this on the graph. Our open loop gain is A sub naught. Our closed loop gain is reduced by this 1 plus t sub 0 factor. Now, why do we do this? Well, we can control the feedback. It's a ratio of resistances. It's much harder to control very precisely the very large gain, A sub 0. So what we do is we trade off stability, and we trade off having a very well-controlled gain for having a very, very large but uncontrolled gain. Now we can also see that our pole frequency was effectively increased. So we can say omega 3 dB, our pole frequency, increased from omega h to omega h prime, and we can show that omega h prime is equal to omega h times 1 plus t sub 0, the loop gain. So that's a good thing. We traded off we traded off a large amount of gain for the feedback to have the stable gain, but we also get more bandwidth from our circuit by doing so. Now, one thing that we should note is that the gain bandwidth product is always constant. And let's validate this. So we know what the gain bandwidth product for the open loop case is A0 times omega t, and we know that the gain times bandwidth product for the closed loop case is A sub 0 divided by 1 plus T sub 0 times omega H times 1 plus T sub 0. And we see, of course, that the 1 plus T sub 0 cancels out, and we're left with omega H, which is, oh, sorry, over here this should be omega H, not omega T, the gain times the bandwidth. Okay, and we know that this product is equal to omega T, our unity gain frequency. So what this tells us is that we can either have high gain or high bandwidth, but not both at the same time. If we want to increase the gain, we would reduce the bandwidth, and if we wanted to decrease the gain, we would increase the bandwidth. So in the next part of the lecture, we're going to look at the telescopic Cascode operational amplifier configuration and do some analysis on the telescopic Cascode amplifier. Telescopic Cascode amplifier is one way that we can increase the amplitude or the magnitude of the gain. We can make the gain much larger, but of course, as we talked about in class, it has some negative side effects, and we'll look at what those are.